This is John Black, Super Chemist. This is a video from a playlist called New and Updated Frames of Reference, and this particular video is part 2 of what is a frame of reference. And remember, in the last video we discussed a frame of reference is just a position or place, where you get your viewpoint from, where you perceive the world from.
We're used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's toss for it. All right? Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. All right.
For the upside down man, for his frame, yeah, he was right side up because his coordinate system was upside down too with him. But both of them were correct. They were both standing up relative to their coordinate system. Yeah, the man who was upside down, why was he telling the truth even though we all know he was upside down? Because he was using a different coordinate system. Instead of him using a coordinate system like this, he used a upside down coordinate system. So relative to this coordinate system, the upside down man was not upside down. Relative to his coordinate system, not relative to Earth. Relative to Earth, he was upside down. When we make measurements, we need to know the reference points. We need to know the frame of reference that those measurements were taken from. Was it taken from the man who was upside down? If it was taken from him, everything's going to be different than the guy who's standing upright on Earth and has a different coordinate system, a different frame of reference. You're going to have different measurements. One's going to be up and one's going to be down, depending on whether your coordinate system is down or up. What do I mean by that, their coordinate system?
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2.
Talking about this thingy right here, we all know what it is, X, Y, Z. They're the spatial dimensions. And this, actually, draw it like this, but we should understand that this is a grid, like down here. The black part is the 2D grid of it, and then I started to do it in red to show that these squares turn into cubes. And these cubes are stacked on top of each other in all 3 directions, X, Y, and Z, and they extend into infinity. Keep in mind, this is just a mathematical construct. It's something we assign, and we arbitrarily assign it, depending on where we are at and what frame we are in. And every person carries around this 3D coordinate system, this fictitious pretend coordinate system that we arbitrarily assign. Now, this stuff about the univectors, I got carried away here. This is actually too advanced. Just forget all about all that. But I do want you to understand this part. When we use this coordinate system, X, Y, we usually don't use this Z axis that comes out of the board. When we use a 2D plane, we just use X and Y, and we use it just like this. But when they go into 3D, your right-hand Cartesian whatever coordinate system, so then you got to use your right-hand rules. And these idiots want you to have it like this. The red is the vertical, or the Y-axis. This would be it like right here. And you can see this white little tiny ball, it's smaller than the other 2. We're going to call it the Z-axis. That's the up axis. And this is the way we usually have it. And this is because we're using just 2D. See, this is supposed to be the up. I want you to think about it when we're using 2D and we don't have this Z here. We can use X and Y and say this one's up and this is over, or the reverse. But when we call X or Y up, we're only using 2 dimensions. So obviously one of them has to be called up. But when you first start out, you're only using a plane. You're only using 2 dimensions. So they don't want to confuse you by saying this is Z and this is X. So they just keep the XY coordinate system and say this is up. But when you actually do have 3 dimensions that you have to calculate in your calculations, I want you to think of it like this. Think of it as like a map. You got north and south. Well, that would be north and east, I'm sorry. But you can see, if you look down on a map, coming out would be up. But in reality, we're looking down. See, we're looking down. If we have it like this, we're looking down on it. Like you're looking down on the map. You're looking down on the ground from above. This is up. So you're looking above it. And what happens is when they want to do 3D, you're going to rotate it so that the Y and the X, and it goes like that. Now you got the X coming out at you. This is actually the way the coordinate system is put, the way they have it set up. So Y is in this direction, X is... This is idiotic, though. This should be always the X, to me, in my mind. Always. And this confuses me every time I got to relearn physics, because then they use these unit vectors and everything's mixed up. Every time they say J hat, I'm thinking it's this axis going up and down. But you can see the x-axis is not here. This is I hat, and this is J hat, because they switch the x and y coordinates. So remember that if you get into 3D stuff, it's very confusing, not because it's confusing, but because they're idiots about how they rotate their coordinate system. And where all the axes line up, they'll intersect right here. That's called the origin. So if you gave numbers to these axes, the origin would be 0 for all 3 number lines. This would be 0. And then you go 1, 2, 3 in this direction, and you go 1, 2, 3 in that direction, and 1, 2, 3 in that direction, and so forth. And going in the opposite direction would give you a negative. Going this way would be negative y. Going this way would be negative z. Going into the board would be negative x. And 1, no matter what it is, whether this is miles or feet, whatever 1 is, that is a unit vector. But if every person carries around this coordinate system, if you move, it moves. This is like attached to your body. Everyone has one. So this would be your frame. Every frame has it, this coordinate system. But when they say, hey, the Earth's frame of reference?
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level.
So on this next experiment, this is a box, and you have this red dot here. And the red dot moves around like a clock hand would. You can see the circle it makes going clockwise. If this apparatus was standing still and you were standing still relative to it, so you're in the same frame of reference, you would see this dot going in a circle. But what if the apparatus moved into a moving frame and you're still standing still and this thing starts moving this way? Will you still see a circle? See, yeah, you will see a circle because you're forcing your mind to. But if you think about it logically, if this moves, this dot will no longer be making a circle because it's moving in the x-axis also.
I want you to watch the motion of this white spot. You probably see the spot moving in a circle.
Anyone who's played with a spirograph, they understand the shape that dot is making.
But this is what its path is actually like in the Earth frame of reference. This is your normal frame of reference. You saw the spot moving in the circle because your eye moved along with the cart. You put yourself in the frame of reference of the moving cart. When the motion is simpler from the moving frame, you automatically put yourself in that moving frame.
Now you remember in part 1, we showed a cart that had a stick on it, and there was a ball attached to the top, and the cart was moving at a constant velocity to the right, and we attached a slow motion camera to the cart, and the ball dropped. And you could see when it was slow motion, it literally went straight down, but we know it was moving at constant velocity, so it moved more like this. And so all you see is down movement. You don't see the X movement because your eyes are moving at the same rate. You are not in the moving frame, but your eyes are moving. So your eyes are in the moving frame of this when it moves. Same way with the cart. Your eyes are moving because you're looking at this. Documentary puts a line there so that you can see it, and then it was so obvious. I was like, how can I not see it? It's because you're, and the same reason up here with this turning thingy here. Why do you see it going in a circle even though you know for a fact it's moving this way, so it can't be moving in a circle? But I want you to notice when they put the camera in the frame of the reference of a standing still like Earth, even then I could not I would swear this ball went straight down along this path of this rod. Yeah, as soon as they drew the line on this, or they drew the line going on this, I could see, boom. Because we were moving at 50 miles an hour, say, and the ball's moving at 50 miles an hour, everything's moving at 50 miles an hour, how could you see it? You can't see any movement into the X dimension when you're moving in the X dimension at the same constant velocity. Because how could you see it? The ball would be right in front of your face if you're looking at it. If you're both going 50 miles an hour, it'd stay at that exact spot relative to you the entire time. This is a John Black postulate. You cannot perceive movement in the direction that you are moving if it is at constant velocity and the thing that you are trying to perceive is also moving at that same constant velocity. You cannot perceive that movement in that same direction, the same direction that you and the ball are moving. Because this is the problem with people have with saying Earth, because Earth is an accelerated frame, but people have this bias where the mind tricks you because you're so used to being in this environment thinking it's inertial. But it's not inertial. And how do we know this? Because we have a rule.
This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. Now, will you give it the same start backwards? I'll try. If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction, and we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall. Now concentrate on watching the puck. Don't let your eye follow us. I think you'll see that it'll move faster that way and not... Now concentrate on watching the puck. Don't let your eye follow us. I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind.
I played that scene 3 times so you can see that motion or velocity is relative. It's a relative thing. It depends on your frame. It depends on your position and your point of view. So next video, that's what we're going to get into. What is relative motion and why do they say all motion is relative? Even though not all motion is relative. Some motion is absolute. And we'll get into that in part 3.